Okay, in this part of the video, we're going to look at what are called phase diagrams. Phase diagrams, quite simply, are graphs. Graphs that will display, based upon pressure and temperature conditions, when a particular chemical will be in its solid phase, when it will be in its liquid phase, or when it will be in its gas phase. Okay. That's all it is. So what you're going to do is every phase diagram has something to this general effect. Now, there's a lot of extra just stuff on here because kind of reminding you of what these terms mean. So the first thing you're going to recognize is right here, there's going to be a solid phase. So part of the diagram somewhere is going to have a line that's separating solids from liquids. And then you're going to have another line that separates liquids from gases. Now you'll notice there's a couple unique points. There's one right here. See the label there, triple point. What that is there's actually a situation where a chemical could exist as a solid and a liquid and a gas. That's what we refer to the triple point. Now the rest of this is again just some things that we can kind of talk about. Obviously, if something is going to melt, it's going to go from a solid phase to liquid. So what will happen is if a particular solid is at pressure X, then how do I get that solid to become a liquid without changing its pressure? Move it to the right. What do I have to do? Increase the temperature. Okay. What if I have, let's say, I have a gas. I have a gas, and I want to turn it into a liquid. But I want it to be maintained at this temperature, whatever Tx is. The only way to get that chemical to turn into a liquid from that point is to raise its temperature something above that value. So that's basically what we're saying is for something to be a liquid, it has to fall in this range right here at those unique temperature and pressure coordinates. If something is going to be a gas, okay, what we have to have is then we'd have to have it at a different temperature and pressure. You can see here, for it to be a gas, then it has to be under these conditions. Again, filling all this in. And then over here we have solids. Another piece that you'll see is you'll also see what's sometimes referred to as the critical point or the critical temperature. And what this means, this is the point where we can no longer change the pressure to make it stay a liquid. We cannot squeeze it enough to make it stay liquefied. So basically what happens is from this point forward, it almost goes just straight up. And everything, and if we can imagine all the way to infinity, there is nothing we can do to make it become a liquid again. Now, the other unique points that you'll want to notice, the curve of these lines. That kind of has that curve. There's kind of that curve to this. These are kind of just generic graphs, but there is some distinction to those lines that we'll see later. Okay. All right. So, and your book has a couple, and we're just going to briefly go through these. Here's the phase diagram for water. If you notice, here's its solid, here's its liquid, there's its gas. You notice right here at 1 atmosphere, this is normal room pressure. That is right in between the liquid and gas phase at a temperature of 100 degrees Celsius. Well, that's when a liquid can go vaporize into a gas, or a gas can condense into a liquid. Right here at this interface, at that intersection, at 1 atm and at 0 Celsius, a solid can melt, a liquid can freeze. Then we have the triple point, which is right down here. And again, you got to kind of watch out for those lines. That is the triple point. That is where at this pressure, so almost no pressure, and at 0 degrees Celsius, we actually can have a mixture of ice, water, and steam. So here's what we want. We got to get it really, really cold to get solid. And we got to kind of keep it cold to get a liquid. But we can't have very much pressure at all. That's how we can then get it to form a gas phase. So it's in what we call equilibrium with each other. We also have a critical point here. So for water, at this temperature, no matter what we do, we cannot change the pressure to get it to stay a liquid. So what ends up happening is from there on out, it's a gas the whole way. Give you another one. Here's carbon dioxide. Looks kind of similar, except here's its triple point. 216 K. 216 Kelvin. If we think about that, 273 Kelvin is 0 degrees Celsius. This is 216. This is almost 60 degrees below zero. Really, really cold. And also, if you notice, 518 kPa, this is about 5 times normal pressure. So carbon dioxide is almost the opposite. We got to have it extremely cold, but at a very high pressure. Why is that? Because there's carbon dioxide is less likely to stay a liquid. So we got to get it cold, okay, to get it to be a solid. But we also got to get it to a lot of pressure to make it stay, for not all of it to change into a gas. Now you'll notice here, if we come back to water, 4.58 torr. We got to take away the pressure so we can get it to be a gas, to get some of that liquid to change into a gas. Carbon dioxide, we got to have it at a really, really high pressure so we can get some of the gas to change back into a liquid. The other thing that you may or may not notice is the curve of the line. It's a forward curve for carbon dioxide, has a slightly negative curve to water. Now, why is that? Think of what water does. It's solid, floats in its liquid. Carbon dioxide, that is not the case. It's solid, does not float in its liquid. So if I take these lines away here, and kind of talk about this. Carbon dioxide is more likely to be a solid than a liquid. Water is slightly more likely to be a liquid than a solid. And this slight curve, again, tells us that this chemical solid will float in its liquid. It's kind of a weird phenomenon from pressure and temperature, but that is one of the things that is unique from that. Another thing that we can look at here is we can also look at, here's one just from more of a more general printout that we can get from a couple different places. Let me show you here an example of where we can get some more images. If you look up on, just go to Google, and you can search phase diagram images, and you're going to see a ton of them. So I'll just quickly do this, and you'll see how the variations of these can apply. So again, you can see all kinds of different diagrams. All right. Now, some are kind of unique, especially because if you're a chemical engineer and things like that. But all these have a purpose. Okay. Some you can see again are very generic, and others are much more complicated, much more intricate. Okay. All right. So one of the things we will talk about then is, as we get into this chapter, we'll also look at dry ice. We'll actually make some dry ice, talk about some of those things and why water acts the way it does, why carbon dioxide acts the way it does, and how we can predict changes and also maybe even cause some changes. All right, so that's it for this section.